Welcome folks, a video today on subspaces. So after an introduction where we make a definition of what makes a subset a subspace, we'll talk about how to test whether a subset is a subspace. We'll see that the span of a set is always a subspace, and then we'll see some other ways to construct subspaces. Okay, so here is the definition of a subspace. Suppose that V and W are vector spaces with identical definitions of vector addition and scalar multiplication. So if V is a subset, if W is a subset of V, then W is called a subspace of V. So there are sort of two things to think about here. First, W is a subset of V, right? So every element that is in W is also in V. And W itself is a vector space, right? So all of those 10 properties then from the definition of what makes a vector space, what makes a collection a vector space, must hold. So of course, if some subsets may be a subspace, of course not all subsets are subspaces. So we'll see examples of some that are and some that aren't. Okay, here is our first example of a subset of C3 that is a subspace. So here is the set W. W is an element of C3. And the rule to be in W is that 2 times its first element minus 5 times its second element plus 7 times its third element is equal to 0. So you can again sort of think of this as a rule to be in the subset W. Okay, so now we have to ask ourselves, is W itself a vector space? And the way that you would check that is to check all 10 properties. So we'll go ahead and verify a couple of them here. Okay, before I get into this additive closure property, I want to point out that it's quick to, for instance, identify an element that is in W, like minus 1, 1, 1 is an element of W. Similarly, 1, 1, 1 is not an element of W. Of course, the zero vector is an element of W, and you can see that pretty quickly too. Okay, so let's go ahead and talk about this additive closure property. Given U and V elements of W, we must have U plus V is an element of W. Okay, so we know how to do vector addition in C3, so let's just write that down first, what U plus V is. So we see that when we have a look at the 2 times the first element of the sum, minus 5 times the second element of the sum, plus 7 times the third element of the sum, that component or that value can be rewritten just using properties of addition over the complex numbers as 2u1 minus 5u2 plus 7u3, which we know is 0, and 2v1 minus 5v2 plus 7v3, which we also know is 0. So we see therefore that the sum u plus v is also an element of W. And it works sort of similarly for closure under scalar multiplication. So given an element u and w, we must have alpha u and w for any scalar alpha. So let's assume that u is in the subset W and have a look at alpha times u. Now, of course, we know how to do scalar multiplication in C3 also. We know that this element alpha u is going to have components alpha u1, alpha u2, and alpha u3. So it had better be that 2 times the first element minus 5 times the second element plus 7 times the third element is 0, and that turns out to be true. Okay, again, just using properties of arithmetic over the complex field, we can see that 2 times the first element minus 5 times the second element plus 7 times the third element is alpha times 2u1 minus 5u2 plus 7u3. And since we've assumed that u is an element of W, it must follow the rule for membership in W. So we see that alpha u is an element of W. Okay, and it turns out that our other properties also hold, so that this subset W is a vector space. It is therefore a subspace of C3. Okay, as it turns out, you don't have to check all 10 properties every time. There's a theorem that tells us whether a subset is a subspace. And it turns out that all you have to check are the previous two definitions. So here's the theorem. When V is a vector space and W is a subset, and W inherits its operations from V, so it has the same definition of vector addition and scalar multiplication, then W is a subspace if and only if it's non-empty, it's closed under vector addition, and it's closed under scalar multiplication. So generally speaking, our subsets W are always non-empty. We don't want to talk about boring subsets. So all you have to do is show this closure under vector addition and show this closure under scalar multiplication in order to show that a non-empty subset is a subspace. Now, of course, if you want to show that a subset is not a subspace, all you have to do is find one counterexample, one set of vectors or one pair of vectors that illustrates it's not closed under vector addition, say, or one set of vectors from the set, one vector from the set such that multiplying by a scalar leaves the set. So here's an example, and we'll go ahead and apply this theorem TSS, testing subsets, to show that, that this subset of P4 is a subspace. Okay, so first we'll show that it's non-empty. Certainly the 0 function is an element of the subset W, so W is non-empty. Okay, so to check closure under vector addition, we'll let P and Q be elements of W. Now, of course, the rule for membership in W in this case is that when you evaluate a function at 2, you get back 0. Okay, so what we want to show then is that their sum is also an element of W. Now, of course, we know how to do vector addition in P4. Vector addition is just function addition in P4. And with vector addition as function addition in P4, we see that P plus Q of X is just P of X plus Q of X, and therefore P plus Q of 2 is just P of 2 plus Q of 2, which of course, since P is an element of W, is 0, and since Q is an element of W, is also 0. Okay, so we see therefore that P plus Q at 2 is 0. It follows the rule for membership in W, so W is closed under vector addition. It works similarly for scalar multiplication. Scalar multiplication in P4, alpha P is defined as alpha times the function P of X. So of course alpha P evaluated at 2 is just alpha times P evaluated at 2. Now again, since P is an element of W, it follows the rule for membership in W, so evaluation of P at 2 gives 0, and therefore we see that alpha P at 2 is also 0. Okay, so this is how one would show that W is closed under scalar multiplication. Since it's closed under vector addition and scalar multiplication, we see that W is a subspace. Okay, here's a subset W, a subset of C2. And it turns out that this subset is not a subspace. So we'll see that just by showing that it turns out it's not closed under vector addition. So what I'll do here is I'll choose 2 elements of W and show that their sum is not an element of W. So here are 2 of those elements. Let's take X to be -1, -3. It's quick to check that X is an element of W. And let's take Y to be 4, 0, 4, 0. So it's also quick to check that Y is an element of W. It's also quick to compute their sum and show that it's not an element of W. Okay, the vector X plus Y is, of course, 3, -3, and 3 times the first element of X plus Y minus 5 times the second element of X plus Y is 24, which is not 12. So we see that X plus Y is not an element of W. W is not closed under vector addition. It works similarly for scalar multiplication. It's pretty quick to show that this subset W is not closed under scalar multiplication either, and I'll let you sort of play with that. Here's another example. X equal to the subset of C2 such that x1 times x2 is equal to 0. It turns out this is not a subspace. So I'll let you try to prove this on the worksheet. This ends up being pretty quick to show, but you have to be a little clever about how you do it. Here's another example of not a subspace. Y is a subset of C2 defined as all integers value x1 and x2. Right, so integers are either positive or negative counting numbers, 1, 2, 3, 4, 5, or -1, -2, -3, -4, -5. It turns out that this subset is closed under vector addition, but it's not closed under scalar multiplication. So I'll let you work that on the worksheet also, see if you can figure out why this subset is not a subspace. We talked about the vector space containing the zero vector. Of course, a vector space is a subset of itself, right? So since a vector space is a vector space, and since the zero vector is a vector space, those are trivial subspaces of the vector space V. Here's an example. Suppose that A is an M by N matrix. The null space of A is always a subspace of Cn. And this is a pretty cool proof because it takes finding that null space back to identifying that there's a vector matrix equation that is equivalent to finding the null space. Okay, so we've started by recasting the null space, which is the set of all solutions to a homogeneous linear system, as the set of all x such that ax equals 0. Now, of course, the zero vector is in this set, so we know that the set is nonempty. So to show that a null space is closed under vector addition, we assume that x and y are elements of the null space. That is, they satisfy the rule to be in the null space, and then we'll have a look at their sum, x plus y. Okay, of course, when we go to check whether x plus y is an element of the null space, we can check that by matrix multiplication by the matrix A. Of course, A times x plus y is the same as ax plus ay, and since x is an element of the null space, ax is 0, and since y is an element of the null space, ay is 0. So we see, therefore, that x plus y is also an element of the null space. The null space is closed under vector addition. It works similarly for scalar multiplication. When x is in the null space and alpha is any scalar, of course, alpha x multiplied by a is alpha times ax. Now, of course, ax itself is an element of the null space, so ax is 0. And I misspoke there. X is an element of the null space, so ax is 0. And of course, alpha times 0 is 0, so we see that alpha x is in the null space and it's closed under scalar multiplication. Okay, so this is kind of a cool deal. Anytime we can recast our rule to be in a subset as a null space, then we can say it's automatically a subspace. So here's an example of that. Here's a subset W such that W members of W satisfy sort of 3 rules for membership. So we can see right away that an element W is an element of the null space of a certain matrix. Okay, any x that is in this subset W satisfies the vector equation ax equals 0 for this matrix A. And again, here I've just picked off the coefficients. Now, of course, any vector x that satisfies ax equals 0 is in the null space of A. So we can see right away, without going through any of the vector addition and scalar multiplication, that W is a subspace. Okay, again, any null space is a subspace, so we see that W is a subspace. I think Beezer has a cool blammo here. You don't have to go through even theorem TSS on this one. We've already done it. Okay, so anytime you can recast a subset as a null space, blammo, that subset is a subspace. Okay, let's talk about the span of a set. It turns out the span of a set is also a subspace. Here's an example where we're thinking about a linear combination of vectors. We can pretty quickly find what 2x plus 4y minus z is for this example. Okay, this is just an example of a linear combination of elements from m to 3. I'll let you work that out at home. But of course, the set of all possible linear combinations is known as the span of a set of vectors. So here is an example that I'll let you work on the worksheet. This theorem tells us that whenever V is a vector space, the span of a set of vectors S is always a subspace. Okay, so the way you prove this is the way that we've proved our other subsets as a subspace. You just have to show that it's closed under vector addition and scalar multiplication. So again, I'll let you work on that on the worksheet. We can talk about it in class too, showing that something is closed under vector addition or scalar multiplication. In this case, requires just showing that the sum of two vectors in the span is also in the span, and that a scalar multiple of a vector in the span is also in the span. Now the take-home message is pretty cool here. Similar to sort of recasting something, some subset as a null space, whenever we can recast a subset as a span of vectors, then that subset is a subspace too. So here's an example. We'll go ahead and cook up a span of vectors within this set W. Okay, so I'm going to pick these two vectors, these two quartic vectors, and let U be the span of those two vectors. Okay, so just to be clear about what we're talking about here, the span of S is the set of all P such that P is equal to alpha 1 P1 plus alpha 2 P2. Now, we know that this span is a subspace, right? Because, well, we've just proved that all spans are subspaces. So, of course, there are some quartic polynomials that are outside the span. So I'll let you go ahead and work this out, but it's pretty quick to show that this element y is not an element of the span of S. Okay, so we can go ahead and cook up some subspaces based on this idea of a span. Okay, for any m by n matrix, the column space of A is a subspace of Cm. To see this, let's just remember the definition of column space. Okay, the column space is the linear combination of all possible linear combinations of columns of the matrix A, right? So the columns of A are going to be denoted here as vectors A1 out to AN, where each A sub I is an element of Cm. So since we're able to represent the column space as the span of a set of vectors, boom, the column space is a subspace. Okay, this is also true for the row space, right? The row space is a subspace because the row space is the column space of the transpose. Okay, every column space is a subspace, so the row space of A is also a subspace. It's a subspace, however, of Cn. The left null space is also a subspace, right? We know that any null space is a subspace, and the left null space is a subspace. The left null space is the null space of the transpose. Okay, so this is pretty cool. Actually, those four subsets that we just talked about at the end of our chapter on matrices are in fact subspaces, right? They themselves are vector spaces. Okay, that's it for this section on subspaces, folks. Hope you've enjoyed learning a little bit about how to tell whether a subset is a subspace, and a few different ways to quickly identify subspaces, right? So spans of sets of vectors are always subspaces, as are null spaces. Have a great day, and we'll see you next time. So long for now. Bye-bye.